Among all the objects astronomers have studied across the universe, one type produces magnetic fields that exceed everything else by an almost unimaginable margin. These objects are called magnetars, and when I first encountered the numbers describing their magnetic strength, the figures seemed almost impossible to accept. A magnetar's magnetic field reaches intensities roughly a quadrillion times stronger than the magnetic field surrounding our own planet Earth. That number, a quadrillion, means a million billion, a 1 followed by 15 zeros, a quantity so large it loses meaning without careful unpacking. The magnetic field of Earth is something we rarely think about, even though it surrounds us constantly and shapes our world in subtle ways. This field guides compass needles, steers charged particles from the sun toward our polar regions where they create auroras, and protects life from radiation. Earth's magnetic field measures roughly half a Gauss in the units scientists use, or about 50 microtesla in the alternative modern units. A magnetar's field reaches 1 billion Tesla or more, which places it in a category that requires new ways of thinking about what magnetism can do. You are listening to the Drowsy Astronaut, and tonight we explore objects that carry the strongest magnetic fields anywhere in the known universe. There is no rush in what follows, no test at the end, no information you must hold on to by morning light. We will simply spend time together learning about these remarkable objects, following the science wherever it naturally leads us through the night. If you enjoy this journey, consider leaving a comment about where you are listening from, and perhaps a like or subscribe if the channel helps you rest. The strength of a magnetar's field becomes easier to appreciate when we compare it to magnets we actually encounter in daily life. A refrigerator magnet produces a field of perhaps 1/100th of a Tesla, strong enough to hold a piece of paper against metal, but gentle to our fingers. The powerful magnets inside MRI machines at hospitals reach 2 or 3 Tesla, strong enough that metal objects become dangerous projectiles if brought too close. A magnetar exceeds even these powerful medical magnets by a factor of 1 billion or more, entering territory where magnetism does strange things to matter itself. At the intensities found around magnetars, the magnetic field begins to affect the very structure of atoms in ways that seem almost fantastical. The electrons that normally orbit atomic nuclei in their usual patterns become distorted, forced into elongated cigars along the direction of the magnetic field. Chemistry, as we understand it, becomes impossible, because the electron arrangements that create chemical bonds cannot maintain their normal configurations. This is not a dangerous environment in the usual sense we might imagine. It is simply a place where the rules of matter that apply on Earth no longer hold. The title of tonight's journey mentions that a magnetar could affect your brain from the distance of the moon, and this claim deserves careful explanation. The magnetic field of a magnetar extends outward from the star in all directions, weakening with distance, but remaining remarkably strong across substantial distances. At a distance equal to the gap between Earth and Moon, roughly 380,000 kilometers, a magnetar's field would still be strong enough to disrupt the electrical signals that neurons use to communicate. This is not about injury or harm, but simply about the scale of what these objects produce, reaching across distances that would seem safely remote by any ordinary standard. The neurons in our brains work through tiny electrical signals, pulses of charged particles moving along cell membranes according to carefully maintained patterns. A magnetic field of sufficient strength affects how charged particles move, potentially disrupting the delicate signaling that produces thought and consciousness. Near a magnetar, even at distances we normally consider vast, the field would interfere with any electrical system, biological or technological. This fact serves as a measure of just how strong the field truly is, not as something to fear, but as something to quietly marvel at. Moving closer to a magnetar in our imagination, the effects of the magnetic field on matter become progressively more extreme and more strange. At distances where the field strength reaches about 100 million Tesla, the electron clouds of atoms become so distorted that atoms themselves take on elongated shapes. The material properties of everything change. Metals behave differently. The way light travels through space is altered. And even the vacuum itself responds. These effects emerge from well-understood physics, but they create conditions that exist nowhere else that we know of in the entire cosmos. Light itself behaves unusually in the presence of such intense magnetic fields, a phenomenon that reveals the deep connection between electromagnetism and the nature of space. Photons traveling through extremely strong fields can split into different polarizations, their oscillations separated by the magnetic influence around them. This effect has a name: vacuum birefringence. But the name matters less than what it represents about conditions near these stars. Space itself, which we normally think of as empty nothingness, responds to the magnetar's field and shapes how light passes through it. The energy stored in a magnetar's magnetic field exceeds the total energy output of the sun over thousands of years. All of it contained around an object smaller than a typical city. This energy does not sit passively, but plays an active role in the magnetar's behavior, driving bursts and flares and shaping the star's evolution over time. The field represents a reservoir of power that the star will draw upon throughout its active life, releasing it in various ways as the years and centuries pass. Understanding where this energy comes from and where it goes requires exploring other aspects of these objects, threads we will follow as our journey continues. The measurement of these magnetic fields happens indirectly, since no spacecraft could survive close enough to measure them directly with instruments. Instead, astronomers observe the light that magnetars emit and look for signatures in that light that reveal the field strength. Certain features in the spectrum of emitted radiation shift in predictable ways, depending on magnetic field intensity, allowing scientists to calculate the field from great distances. The precision of modern instruments has confirmed that magnetars truly possess these extraordinary fields, transforming what once seemed like theoretical speculation into observed fact. When astronomers first began detecting objects that would later be identified as magnetars, the extreme field strengths required to explain the observations seemed almost too extreme to be real. The physics community debated whether any natural process could create such intense magnetism, questioning whether other explanations might fit the data better. Over decades of observation and theoretical work, the magnetar explanation proved correct, and these objects took their place among the confirmed wonders of the universe. The magnetic fields are real, they are measured, and they exceed anything else we have found by enormous margins. The units scientists use for magnetic field strength have an interesting history that connects to the development of electromagnetism as a science. The Gauss, named after the mathematician Carl Friedrich Gauss, measures magnetic field strength in the older CGS system of units still common in astronomy. The Tesla, named after the inventor Nikola Tesla, serves as the standard unit in the modern SI system that most sciences now use. Converting between them is straightforward. 1 Tesla equals 10,000 Gauss, but the numbers describing magnetars reach into the billions regardless of which unit we choose. To hold the strength of a magnetar's field in mind, it helps to build a ladder of comparisons, climbing from the familiar to the extreme. Earth's field sits at the bottom, about half a Gauss, enough to slowly align compass needles pointing toward magnetic north. A typical bar magnet reaches perhaps 100 Gauss, 1,000 times stronger than Earth, and enough to pick up paper clips. Medical MRI machines operate at 20,000 to 70,000 Gauss, strong enough to require careful protocols about bringing metal objects near them. Industrial magnets used in research can reach 500,000 Gauss, approaching the limits of what current technology can produce without destroying itself. The magnetic fields of ordinary neutron stars, already extreme by any standard, reach 1 trillion Gauss, roughly 100 million times stronger than the strongest laboratory magnets. Magnetars then exceed even these already extraordinary neutron stars by another factor of 100 to 1,000, reaching 10 quadrillion Gauss at the surface. Each step on this ladder takes us further from everyday experience, but the physics remains consistent, just operating at scales we cannot directly perceive. This magnetic field does not simply exist as an abstract property. It emerges from a physical surface and extends through a physical space. The object producing this field is a type of neutron star, a collapsed remnant of what was once a massive star many times larger than our Sun. The surface from which these magnetic field lines emerge is unlike any surface we could stand upon, made of material compressed to densities beyond ordinary imagination. What that surface looks like, what it is made of, and what conditions exist there will carry us into the next phase of our exploration. The surface of a magnetar presents one of the strangest landscapes anywhere in the known universe. A place where conditions depart so far from Earth that description requires careful translation. Unlike the Sun and most stars, which have no true surface, but rather gradual transitions from denser to thinner gas, a magnetar has a solid outer layer. This solid shell is called the crust, and it is made of material compressed to densities that sound like fiction, but emerge from well-established physics. A single teaspoon of this material, if somehow transported to Earth, would weigh roughly 1 billion tons, comparable to the mass of a small mountain. The density at the surface of a magnetar reaches about 1 million grams per cubic centimeter, roughly 1 million times denser than ordinary water. This crushing compression occurs because the gravitational pull of the star is immense, perhaps 200 billion times stronger than Earth's gravity at the surface. Anything that fell toward this surface would accelerate to substantial fractions of the speed of light before impact, arriving with energies that would vaporize any ordinary material. The surface endures these conditions because it is made of matter in a form that exists nowhere else under natural conditions that we can observe. The atoms in the magnetar's crust have been compressed until they no longer resemble the atoms we know from chemistry and everyday experience. Under normal conditions, Atoms are mostly empty space, tiny nuclei surrounded by electron clouds that extend far from the center. In the magnetar's crust, this empty space has been squeezed out, and the nuclei are packed close together in a rigid, crystalline arrangement. The electrons have been forced to occupy much smaller regions, and some have merged with protons to become neutrons, leaving behind material rich in neutrons and unlike any substance found on Earth. This crystalline structure of compressed nuclei gives the crust remarkable properties, including strength that exceeds any material we can manufacture. The crust is estimated to be roughly 1 billion times stronger than the strongest steel produced in human factories, capable of withstanding tremendous forces before fracturing. This strength will become important later when we explore what happens when the crust finally does break. But for now, it suffices to know that this material resists deformation with astonishing stubbornness. The magnetic field lines threading through this crust are anchored firmly, held in place by material that refuses to yield except under the most extreme circumstances. The temperature at the surface of a magnetar typically reaches about 1 million degrees Celsius, hot enough to glow intensely across much of the electromagnetic spectrum. Despite this extreme temperature, the surface remains solid rather than melting or vaporizing into gas, a seemingly paradoxical situation that deserves explanation. The tremendous pressure at the surface keeps the material locked in its crystalline state, even at temperatures that would vaporize any normal substance. Pressure and temperature together determine whether material is solid, liquid, or gas, and the pressure here overwhelms the temperature completely. The glow from this hot surface emerges primarily as X-rays, a form of light with wavelengths much shorter than visible light and energies much higher. Human eyes cannot see X-rays, which is fortunate since they would be damaging to our biology if we could perceive them directly. To observe a magnetar's surface glow, astronomers must use telescopes placed above Earth's atmosphere, which blocks most X-rays from reaching ground-based instruments. From these orbiting observatories, the hot surfaces of magnetars shine clearly against the X-ray sky, revealing their temperatures and other properties through careful analysis. The magnetic field lines emerge from the surface in patterns that depend on the field geometry within the star, rising outward into the space surrounding the magnetar. These lines are not visible to any instrument, but we can picture them as threads or streams extending from the poles and curving around toward the equator. In some magnetars, the field may be relatively simple, resembling a bar magnet with clear north and south poles at opposite ends. In others, the field may be twisted and complex, wound around itself in configurations that store enormous amounts of energy, waiting to be released. The curvature of the magnetar's surface is much more pronounced than the curvature of larger worlds, because these stars are so remarkably small. A typical magnetar measures only about 20 kilometers across, smaller than many cities on Earth, and far smaller than any planet. Standing on this surface, a thought experiment only, since survival would be impossible. The horizon would appear much closer than on Earth, curving away visibly in all directions. The sky above would be black and filled with stars, since magnetars have no significant atmosphere to scatter light into blue or any other color. Despite the incredible gravitational forces flattening everything towards perfect smoothness, the surface may not be entirely featureless. Small mountains or ridges might exist, though they would be measured in centimeters rather than kilometers, any taller structures having been crushed by gravity long ago. The magnetic field might create subtle variations in the surface properties, with some regions slightly different from others in ways that affect how the star emits radiation. These small-scale features, if they exist, are far beyond our current ability to observe directly, but theoretical models suggest they may play roles in the star's behavior. The landscape, if we can call it that, would appear as a glowing plain stretching to that nearby horizon, illuminated not by any external source, but by its own tremendous heat. The glow would be essentially uniform in color to any eye capable of perceiving X-rays, a blue-white radiance emerging from the crystalline surface. The magnetic field, invisible but dominating everything, would shape how any particle or photon moved through the region immediately above the surface. This is not a quiet place, despite the apparent stillness. Processes occur here that influence the star's behavior and that occasionally erupt into events detectable across the galaxy. The crust extends downward for perhaps 1 to 2 kilometers before giving way to even more exotic material beneath. This thinness, a crust only 1 or 2 kilometers thick on a star 20 kilometers across, means the surface layer is proportionally thinner than the skin of an apple. Below this thin outer shell, the conditions become even more extreme, with densities and pressures that push matter into truly unfamiliar states. The journey from surface to core takes us through materials that exist only in neutron stars, substances so strange they challenge our ability to describe them adequately. Gravity shapes everything about this surface, and the star it covers, pulling with a force that determines what can exist and what cannot. The escape velocity at the surface, the speed needed to leave the star's gravitational grip, reaches roughly half the speed of light, making this one of the most gravitationally dominated surfaces in the universe. Only black holes exceed neutron stars in gravitational intensity, and black holes have no surfaces in the conventional sense at all. The magnetar's surface represents the most extreme solid surface we know of, a boundary between starlight and the crushing depths below. The solid crust floating on whatever lies beneath moves as a single piece, rotating with the star as it spins through space. Magnetars typically rotate more slowly than other neutron stars, completing one rotation every few seconds, rather than many times per second. This rotation means different parts of the surface pass through the observer's view in sequence, creating the pulsations that help astronomers study these objects. The hotspots, or active regions on the surface, come into view, then rotate away, then return on the next rotation in a repeating pattern. As the surface rotates and glows, and the magnetic field extends outward, the processes occurring in the crust connect to the deep interior below. The magnetic field anchored in the crust extends downward through layers of increasingly compressed matter, threading through material unlike anything found elsewhere. What happens in the interior affects the surface, and what happens on the surface can disturb the interior, creating connections that drive the magnetar's behavior. The journey continues inward now, descending from this crystalline outer layer into regions where matter takes forms that stretch our understanding of physics. Beneath the solid crust of the magnetar lies an interior so compressed that matter exists in states found nowhere else in the natural universe, except inside neutron stars. The transition from crust to interior happens across a relatively short distance, perhaps only a kilometer or two below the surface we just explored. As we descend through this thin crust in imagination, the density increases steadily, and the atomic nuclei that make up the crustal material begin to change shape. The deeper we go, the more extreme the compression becomes, and the more unfamiliar the matter appears. In the outer crust near the surface, atomic nuclei still resemble recognizable nuclei, though they are packed much closer together than in ordinary matter. These nuclei are arranged in a crystalline lattice, held in fixed positions by the electromagnetic forces between them, while electrons flow relatively freely between. Moving deeper, the nuclei become increasingly rich in neutrons, as the intense pressure forces electrons and protons to combine into neutrons. This process, called electron capture, gradually transforms the composition of the material as depth increases. The inner crust begins where neutrons start to drip out of the nuclei entirely, unable to be contained within the nuclear boundaries any longer. These free neutrons form a fluid that permeates the spaces between the remaining nuclei, creating a mixture of solid nuclear structures swimming in a neutron sea. This region behaves in ways that combine properties of both solids and fluids, with the nuclei locked in place while the neutrons flow around them. The exact boundary between outer crust and inner crust lies perhaps half a kilometer to a kilometer below the surface, depending on the specific star. As we continue descending, the nuclei themselves begin to deform under the incredible pressure, losing their roughly spherical shapes. Instead of remaining as compact spheres, the nuclei stretch into elongated forms, creating structures that physicists have named after familiar foods because of their shapes. The first of these exotic arrangements is called gnocchi, referring to small potato-like lumps of nuclear matter scattered through the neutron fluid. These lumps are what remains of the nuclei, distorted by pressure, but still maintaining some separate identity. Deeper still, the gnocchi merge and elongate into long tubes of nuclear matter running through the neutron fluid like strands of pasta. These tube-like structures are called spaghetti, and they represent a further breakdown of the distinction between individual nuclei and the surrounding neutron sea. The spaghetti strands contain protons and some neutrons bound together, while the fluid between them consists primarily of free neutrons with some electrons mixed in. This layered mixture creates mechanical properties unlike anything found in ordinary engineering materials, or even in exotic laboratory conditions. Continuing our descent, the spaghetti tubes merge into sheets of nuclear matter, flat planes extending through the neutron fluid and separated by gaps. These flat sheets are called lasagna, continuing the pasta naming convention that physicists have adopted with some apparent amusement for these structures. The lasagna sheets contain the remaining protons surrounded by neutrons, while the gaps between sheets consist almost entirely of neutron fluid. The transition from spaghetti to lasagna happens smoothly as pressure increases, with the tubes gradually flattening and merging. Below the lasagna region, the geometry inverts. Instead of nuclear matter forming sheets surrounded by neutron fluid fills tubes surrounded by nuclear matter. These anti-spaghetti structures are sometimes called bucatini, after the hollow pasta, though the naming becomes increasingly playful at these depths, where direct observation is impossible. The final pasta phase consists of spherical bubbles of neutron fluid surrounded entirely by nuclear matter, the inverse of the gnocchi configuration from higher levels. These phases together are collectively called nuclear pasta, and they likely comprise the strongest material in the universe. The pasta phases give way eventually to a uniform fluid as we approach the outer core of the neutron star, the nuclei finally losing all distinct identity. In this outer core region, matter consists of neutrons, protons, electrons, and possibly other particles, all mixed together in a single fluid. The neutrons vastly outnumber the protons, typically comprising about 95% of the matter, with protons, electrons, and other particles making up the remainder. This fluid is not ordinary liquid. It likely exists in a quantum state called superfluidity, where it flows without any friction or resistance. Superfluidity is a property that emerges at extremely low temperatures in ordinary materials, but in neutron stars, it persists even at temperatures of millions of degrees. The extreme density creates conditions where quantum effects dominate the behavior of matter, allowing the superfluid state to exist despite the tremendous heat. A superfluid can flow through any gap without losing energy, can rotate in strange quantized patterns called vortices, and exhibits other counterintuitive behaviors. The neutron fluid in the outer core likely carries angular momentum through millions of tiny vortex lines threading through the star. The protons in the outer core may exist in their own unusual state, called superconductivity, where they conduct electricity with absolutely zero resistance. In ordinary superconductors, which require extremely cold temperatures on Earth, electrical currents can flow forever without any energy loss once started. The superconducting protons in the neutron star core contribute to how the magnetic field behaves within the star, anchoring field lines and affecting the star's long-term evolution. The combination of superfluid neutrons and superconducting protons creates an interior unlike anything we can study directly in laboratories. The inner core remains the most mysterious region, where densities exceed anything we can simulate or observe through other means. At the very center of the magnetar, densities may reach 5 to 10 times the density of atomic nuclei, crushing matter into states we cannot predict with certainty. Some theories suggest that neutrons and protons might break down into their constituent quarks, creating a fluid of free quarks unlike any matter observed elsewhere. Other theories propose different exotic states, including strange matter containing a type of quark not found in ordinary protons and neutrons. The uncertainty about the inner core reflects the limits of our current understanding of matter under such extreme conditions. The pressures and densities involved exceed what particle accelerators can create, even in the brief moments of heavy ion collisions designed to study extreme matter. Neutron stars serve as natural laboratories for these conditions, but we observe them only from the outside, inferring interior properties from surface behavior. The magnetic field, threading through all these layers, connects the mysterious core to the observable surface, carrying information we have only begun to decode. Throughout this interior, the magnetic field that makes magnetars special extends from surface to core, threading through the pasta phases and the superfluid regions. The field may be anchored primarily in the superconducting proton component, held in place by currents that circulate without resistance through the outer core. In magnetars, the field strength remains immense. Even in the deep interior, exceeding the fields of ordinary neutron stars by the same factor as at the surface. How this extraordinary field interacts with the exotic matter around it drives much of what makes magnetars behave as they do. The total size of all these layers combined, crust, pasta, outer core, inner core, amounts to a sphere only about 20 kilometers across. This entire journey from surface to center, which we have traced through several paragraphs, covers a physical distance roughly equal to the length of Manhattan Island. Yet this small sphere contains more mass than the Sun, compressed into a volume that would fit easily inside any major city on Earth. The compression is what creates all the exotic states we have explored, gravity pressing matter into configurations it could never achieve without such tremendous force. This extraordinarily compressed object, with its exotic interior and solid crust and extreme magnetic field, did not always exist in this form. Every neutron star began its existence as something much larger and more ordinary, a massive star burning fuel in its core. The transformation from ordinary star to neutron star happens in one of the most energetic events in the universe, a process that takes only seconds to complete. Understanding how magnetars form requires stepping back to see the death of the massive star that becomes this compact remnant. The magnetar we have been exploring belongs to a category of objects called neutron stars, all of which share certain fundamental properties regardless of their magnetic field strength. Understanding what makes any neutron star requires understanding the extreme compression that creates them, the physics that allows them to exist in stable form. This foundation will help us appreciate what makes magnetars special among an already extraordinary class of objects. The compression itself emerges from one of the fundamental forces of nature, gravity, overpowering everything else. Gravity is the weakest of the fundamental forces, easily overcome by the other forces in everyday circumstances. A small magnet can lift a paperclip off a table, overcoming the gravitational pull of the entire Earth with barely any effort. An atom holds together against gravity with electromagnetic forces that exceed gravitational attraction between its components by factors too large to easily express. In ordinary situations, gravity matters only when enormous masses are involved, pulling planets into orbits and holding galaxies together while being irrelevant at atomic scales. In a neutron star, gravity has won decisively, overwhelming the other forces through sheer accumulated mass and compressing matter to its limits. The mass involved, roughly 1.5 times the mass of our Sun, creates gravitational force sufficient to crush atoms themselves. This crushing eliminates the empty space that makes ordinary atoms mostly vacuum, forcing the nuclei and electrons into configurations much more compact than any normal matter. The result is material roughly 100 trillion times denser than water, packed into a sphere smaller than most cities. The compression cannot continue indefinitely. Something must eventually resist the inward force of gravity, or the object would collapse to a point. In ordinary stars like the Sun, the outward pressure comes from hot gas heated by nuclear fusion, balancing gravity through thermal energy. In white dwarf stars, the remnants of smaller stars that have exhausted their fuel, a quantum mechanical effect called electron degeneracy pressure provides the resistance. Electrons resist being squeezed into the same quantum state, creating an outward pressure that halts collapse even when fusion has ceased. For objects more massive than white dwarfs can support, electron degeneracy pressure proves insufficient, and gravity overwhelms the electrons entirely. The electrons are forced to combine with protons, forming neutrons and eliminating the electron degeneracy pressure that might have halted collapse. At this point, a new form of resistance emerges: neutron degeneracy pressure, a similar quantum mechanical effect, but operating on neutrons instead of electrons. This pressure halts the collapse and creates the stable neutron star configuration, a balance between gravity and quantum mechanics that can persist for billions of years. The quantum mechanical principle underlying both electron and neutron degeneracy pressure is called the Pauli exclusion principle, named after the physicist Wolfgang Pauli. This principle states that no two identical particles can occupy exactly the same quantum state at the same time. When particles are compressed into a small space, they are forced into higher and higher energy states to avoid violating this principle, which requires energy to achieve. The resistance to further compression manifests as an outward pressure, balancing the inward pull of gravity and creating a stable configuration. A neutron star represents matter compressed to approximately the density of an atomic nucleus, as if a giant atomic nucleus, the size of a city, existed in space. The material is not actually a single giant nucleus. The structure is more complex, as we explored in the previous part, but the density comparison helps convey the compression involved. If the entire Earth were compressed to neutron star density, it would become a sphere less than 100 meters across, a ball you could walk around in a few minutes. The Sun, compressed to this density, would become a sphere about 20 kilometers across, which is approximately what happens when massive stars die. The mass required to create a neutron star comes from stars significantly more massive than our Sun, typically at least 8 to 10 times the solar mass originally. Smaller stars cannot compress their cores sufficiently during their death throes to reach neutron star densities, instead becoming white dwarfs through gentler processes. The dividing line between white dwarf formation and neutron star formation depends on the star's mass throughout its life, particularly the mass of the core when fusion finally ceases. Stars above this threshold face a dramatically more violent end, one that compresses their cores while scattering their outer layers into space. Approximately 2,000 neutron stars have been identified in our galaxy, though the actual population is certainly much larger than what we have detected. Most known neutron stars are detected as pulsars, rapidly rotating objects that sweep beams of radiation across our view, like lighthouse beams. The rotation can be astonishingly fast. Some pulsars spin hundreds of times per second, their surfaces moving at significant fractions of the speed of light. This rapid rotation is a remnant of the original star's rotation, speeded up enormously by the conservation of angular momentum during collapse. When a spinning object contracts, it must spin faster to conserve the total angular momentum it carries, just as an ice skater spins faster when pulling in their arms. A star that rotated once per month might collapse into a neutron star rotating many times per second, speeding up by a factor of millions during the compression. The magnetic field similarly intensifies during collapse, compressed along with the matter and emerging much stronger than it began. Both rotation and magnetic field are amplified by the collapse, reaching intensities impossible to achieve through any other known process. Among the roughly 2,000 known neutron stars, magnetars represent a small minority, perhaps 30 confirmed objects, depending on how the boundaries are drawn. What distinguishes a magnetar from an ordinary neutron star is the magnetic field strength, which exceeds typical neutron star fields by factors of 100 or more. Ordinary neutron stars have fields around 1 trillion Gauss, already enormously strong by any terrestrial standard, but modest compared to magnetar fields. Magnetars push into the 10 quadrillion Gauss range, where the field begins to affect the structure of matter and the nature of empty space itself. The question of why some neutron stars become magnetars while others become ordinary pulsars remains an active area of research among astronomers. The conditions at birth seem to matter: the properties of the original star, the details of the collapse, the rotation rate in the first seconds. Something in these early moments sets a neutron star on a path toward ordinary pulsar behavior, or toward the extreme magnetism that defines magnetars. The formation process, occurring in one of the most energetic events known to physics, holds the key to understanding these differences. Every neutron star forms in a supernova, the explosive death of a massive star that scatters outer layers into space, while crushing the core into compressed matter. The energy released in a supernova briefly outshines entire galaxies, marking the transformation from ordinary star to compact remnant. This violent birth takes only seconds, from the moment of core collapse to the formation of the neutron star, though the visible explosion continues for weeks or months. Understanding what happens in those crucial seconds helps explain how magnetars emerge from the chaos of stellar death. The transformation of a massive star into a magnetar begins with a stellar life that differs markedly from the gentle existence of stars like our Sun. Stars that will eventually produce neutron stars start with masses at least 8 times greater than the Sun, burning through their nuclear fuel far more rapidly. Where the Sun will shine for about 10 billion years before exhausting its hydrogen, these massive stars consume their fuel in mere millions of years. Their lives are brief by stellar standards, bright and fast, ending in the spectacular collapse that creates the compact remnants we have been exploring. During its life, a massive star fuses hydrogen into helium in its core, then helium into carbon, then carbon into heavier elements in a sequence of nuclear reactions. Each stage produces energy that supports the star against gravitational collapse, maintaining the balance that keeps the star shining. The fusion products from each stage become the fuel for the next, as the core grows hotter and denser with each transition. The star develops a layered structure, with different elements fusing in shells surrounding an ever heavier core, like layers of an onion made of nuclear fire. The final stage of nuclear fusion in a massive star produces iron in the core, and iron marks the end of the energy-producing line. Unlike lighter elements, iron cannot release energy through fusion. Fusing iron absorbs energy rather than releasing it, providing no outward pressure to fight gravity. When the core becomes iron, the energy source that has supported the star for millions of years simply stops, and gravity suddenly has no opposition. What happens next unfolds in less than a second, transforming a core larger than Earth into a neutron star, smaller than a city. The core collapses at roughly 1/4 of the speed of light, falling inward so rapidly that the outer layers initially cannot follow. Matter streams toward the center, compressing and heating to temperatures exceeding 100 billion degrees, hotter than any other place in the present-day universe. At these temperatures and densities, the iron nuclei that took millions of years to build are torn apart in an instant, undoing the work of stellar fusion. Protons and electrons merge into neutrons as the collapse continues, forming the neutron-rich matter that will become the neutron star. The collapse halts abruptly when neutron degeneracy pressure finally provides sufficient resistance to stop the compression, creating a shock wave at the core boundary. This shock wave propagates outward into the still falling outer layers, reversing their motion and ejecting them into space at thousands of kilometers per second. The visible supernova is this explosion of the outer layers, material that will eventually form nebulae and contribute to future generations of stars and planets. Behind the explosion, the newly formed neutron star remains, incredibly hot and rotating rapidly, beginning its long existence as a compact remnant. The neutron star, at the moment of its formation, is extraordinarily different from what it will become millions of years later. The temperature exceeds 100 billion degrees, far hotter than the core of any normal star, radiating energy furiously in neutrinos and later in other forms. The rotation rate may reach 1,000 times per second, the star spinning so fast that its surface moves at significant fractions of the speed of light. The magnetic field is still being established, amplified by the tremendous energies swirling through the newly compressed matter. The amplification of the magnetic field during and immediately after collapse is the key process that determines whether a neutron star becomes a magnetar or an ordinary pulsar. One mechanism involves the dynamo effect, similar in principle to how Earth generates its magnetic field, but operating under far more extreme conditions. Rapid rotation, combined with turbulent convection in the hot neutron star interior, can amplify weak seed fields into the extreme fields characteristic of magnetars. This process must work within seconds to minutes of the neutron star's formation, while conditions are suitable for efficient amplification. For the dynamo to create a magnetar, the neutron star must be rotating fast enough, perhaps 300 or more times per second, during the critical early phase. Stars that rotate more slowly at birth may lack the necessary conditions for extreme field amplification, instead becoming ordinary pulsars with more modest fields. The rotation rate at birth depends on the angular momentum of the original star's core, which relates to how the star evolved and possibly to interactions with companion stars. The path to becoming a magnetar may be set long before the supernova itself, encoded in the original star's properties. An alternative theory suggests that the extreme magnetic field is not created anew during collapse, but rather inherited from the original star and compressed along with the matter. Some massive stars possess unusually strong magnetic fields during their lives, and these fields would intensify during the compression of the core. The magnetic field strength increases as the square of the compression ratio, meaning a collapse from thousands of kilometers to 20 kilometers would amplify the field by factors of millions or billions. This compression could bring a moderately strong stellar field up to magnetar levels without requiring any dynamo action. Both mechanisms may contribute to creating magnetars, with different stars following different paths to similar outcomes. The observational evidence cannot yet distinguish clearly between these possibilities, and theoretical models continue to be refined and tested. What we can observe is that some neutron stars emerge from supernovae with extreme magnetic fields, while others do not, indicating that something in the formation process differs between them. The exact conditions that produce a magnetar rather than an ordinary pulsar remain an open question, inviting continued research and observation. The supernova itself may be affected by the formation of a magnetar within it, potentially becoming more energetic or longer lasting than ordinary supernovae. The magnetic energy stored in a newborn magnetar can exceed the kinetic energy of the supernova explosion, providing additional power to the ejected material. Some unusually bright supernovae may be explained by magnetars spinning down rapidly after formation, dumping rotational energy into the surrounding explosion. These so-called superluminous supernovae might serve as signposts indicating magnetar formation, though alternative explanations exist for their extreme brightness. The newly formed magnetar, still incredibly hot and rotating rapidly, begins to cool and slow down immediately after birth, starting processes that will continue for millions of years. The cooling happens through neutrino emission initially, then later through photon radiation as the surface temperature drops. The slowing happens as the rotating magnetic field radiates energy into space, converting rotational kinetic energy into electromagnetic waves. Both processes are inevitable consequences of physics, drawing energy from the newborn star and releasing it into the universe around it. Within the first days and years, the magnetar's rotation slows significantly, though it remains faster than it will be millions of years later. The extreme magnetic field places enormous stresses on the solid crust, stresses that build over time as the field configuration slowly evolves. These stresses eventually exceed what even the strongest material in the universe can withstand, leading to sudden fractures that release tremendous energy. The magnetar has begun its active life, a period of bursts and flares that will gradually diminish as the magnetic field weakens over thousands of years. The solid crust of a magnetar exists under constant stress from the extraordinary magnetic field threading through it, a tension that builds steadily over time. The magnetic field is anchored in the deep interior of the star, held in place by currents in the superfluid and superconducting layers below the crust. At the same time, the field must pass through the crust to emerge at the surface, creating a situation where the rigid outer layer feels the pull of forces rooted deep within. As the interior magnetic field evolves slowly over months and years, the crust must either deform to accommodate or eventually fracture under the accumulated stress. The crust resists deformation with extraordinary tenacity, its crystalline structure giving it strength that exceeds any material found on Earth by factors of 1 billion or more. This strength comes from the nuclear forces binding the compressed nuclei in their lattice positions, forces vastly stronger than the chemical bonds holding ordinary materials together. The crust can endure stresses that would instantly shatter any substance we can manufacture, maintaining its integrity against forces that seem overwhelming by terrestrial standards. Yet even this incredible material has limits, and the magnetic field of a magnetar is capable of exceeding them. The stress accumulates unevenly across the crust, concentrating in some regions while remaining lower in others, depending on the geometry of the magnetic field. Where the field is strongest, or most twisted, the stress on the crust reaches its highest values, creating zones of potential failure. The situation resembles, in some ways, the buildup of stress along earthquake faults on Earth. though the physics differs fundamentally, and the energies involved are incomparably greater. The crust remains intact for months or years at a time, but the stress continues to build, approaching the breaking point with each passing interval. When the stress finally exceeds what the crust can withstand, the material fractures suddenly, releasing the accumulated elastic energy in a burst. This fracture is called a starquake, and it represents one of the most energetic processes that can occur on a neutron star surface. The crack propagates across the crust at a significant fraction of the speed of light, covering kilometers in milliseconds as the material shifts to relieve the stress. The displacement may be only centimeters or even less, but the energy released by even this tiny motion is extraordinary. The energy released in a large starquake can exceed the total energy output of our sun over an entire year, all delivered in a fraction of a second. This comparison helps convey the scale of the event, but it risks suggesting something violent or dangerous in a way the actual phenomenon does not warrant. The energy release is simply the conversion of magnetic and elastic potential energy into other forms: heat, light, and accelerated particles. The star itself continues essentially unchanged afterward, its mass and overall structure unaffected by what is essentially a very energetic surface adjustment. The crust moves to a new configuration during the starquake, one that better accommodates the current state of the internal magnetic field. After the quake, the stress is temporarily relieved in the affected region, and the crust settles into its new arrangement. The magnetic field lines that thread through the crust shift as well, their geometry altered by the motion of the material they are anchored in. This reconfiguration may be observable as a sudden change in the star's spin rate, or as a burst of radiation accompanying the quake itself. Scientists detect starquakes primarily through their effects on the magnetar's rotation, which can change suddenly during or immediately after a fracture event. The rotation rate typically increases slightly during a starquake, a phenomenon called a glitch, as the crust shifts and angular momentum is redistributed within the star. These glitches are measured in parts per million changes to the rotation period, tiny fractions that nonetheless represent enormous changes in angular momentum at this scale. The pattern of glitches over time provides information about conditions in the crust and the rate of stress accumulation from the magnetic field. The radiation released during starquakes comes from several processes triggered by the sudden fracture and field reconfiguration. The shifting magnetic field accelerates charged particles near the surface, and these particles emit radiation as they spiral along the field lines. The crust itself may heat locally at the fracture site, producing additional thermal radiation visible in X-rays. The combination of these processes creates a burst of emission that can be detected by space-based observatories, tuned to the appropriate wavelengths. Smaller starquakes may occur frequently, perhaps daily or even more often, releasing modest amounts of energy and causing minor adjustments to the crustal configuration. Larger starquakes are rarer, separated by months or years, but release correspondingly greater amounts of energy when they occur. The distribution of starquake sizes follows statistical patterns that scientists use to understand the mechanical properties of the crust and the rate of magnetic stress accumulation. Each starquake provides a window into conditions on and beneath the surface that cannot be observed directly. After a starquake, the cycle of stress accumulation begins again, the magnetic field continuing to evolve and the crust gradually feeling the renewed pull. The same region may experience repeated quakes over time, or the next fracture may occur in a different location where stress has built to critical levels. The entire surface is subject to this process, though some regions may be more prone to quakes than others, depending on local field geometry. The magnetar's life is punctuated by these events, quiet intervals separated by sudden adjustments as the crust accommodates the restless magnetic field within. The relationship between the magnetic field evolution and crustal fracturing drives much of the magnetar's observable behavior during its active lifetime. The field cannot change freely because it is anchored in the superconducting interior, but it cannot remain static because internal processes inevitably alter its configuration. The crust mediates between these constraints, deforming slightly when possible, and fracturing when deformation is insufficient to relieve the stress. This dynamic interaction produces the bursting behavior that characterizes magnetar activity, a signature that distinguishes them from other neutron stars. The energy stored in the magnetic field provides the reservoir that powers starquakes and the bursts that accompany them. A magnetar's field contains more energy than the sun produces over thousands of years, all locked in the invisible lines of force extending through and around the star. Each starquake draws from this reservoir, converting magnetic energy to radiation and heat, gradually depleting the field over the star's active lifetime. The field is not destroyed but weakened, its intensity decreasing over thousands of years as energy is released in bursts and continuous emission. While ordinary starquakes release energy exceeding the sun's annual output, even larger events sometimes occur that dwarf typical quakes by many orders of magnitude. These giant flares represent the most extreme releases of electromagnetic energy known to occur anywhere in the universe, briefly outshining entire galaxies in gamma rays. The mechanism involves more than simple crustal fracturing. Something more catastrophic must occur to release so much energy so quickly. Understanding giant flares requires examining the most extreme events that magnetars produce, events that have been observed from across the galaxy and beyond. 3 times in the decades since astronomers began detecting them, magnetars have produced bursts of energy so extreme that they stand apart from all other magnetar activity. These events are called giant flares, and they release more energy in a fraction of a second than our sun produces over hundreds of thousands of years. Only 3 have been confirmed from magnetars in our galaxy, or its nearest neighbor galaxies, making them among the rarest observed phenomena in high-energy astronomy. The most powerful of these occurred on the 27th of December, 2004, an event that affected instruments throughout the solar system, despite originating nearly 50,000 light-years away. The magnetar responsible for the December 2004 event carries the catalogue designation SGR 1806 Destiny, a name derived from its sky coordinates and classification as a soft gamma repeater. This object sits on the far side of our galaxy, hidden behind dust and gas at visible wavelengths, but easily detected in X-rays and gamma rays. The distance of 50,000 light-years means the light from this flare traveled for 50,000 years before reaching Earth, the event itself occurring when our ancestors were painting cave walls. Despite this enormous distance, the flare's effects were measurable here in our solar system. The initial spike of the flare lasted only about 0.2 of a second, a brief flash that saturated gamma-ray detectors throughout the inner solar system. In that fraction of a second, the magnetar released approximately 10 to the 46th power ergs of energy, a number that requires context to appreciate. This energy equals what the sun produces over roughly 250,000 years of steady shining, released in less time than it takes to blink. For a moment, this single object on the far side of the galaxy outshone everything else in the gamma-ray sky combined. The flash ionized the upper layers of Earth's atmosphere, despite the vast distance, a measurable effect caused by gamma rays and X-rays arriving from across the galaxy. Satellites in orbit detected the pulse, and in some cases, experienced temporary effects on their instruments and operations. If the magnetar had been located much closer, say 10 light-years away instead of 50,000, the effects on Earth would have been far more significant, potentially damaging the ozone layer and affecting life on the surface. The December 2004 event demonstrated that magnetars can influence their galactic neighborhoods across distances that might otherwise seem safely remote. Following the initial spike, the emission continued in a pulsating pattern that revealed the magnetar's rotation period of about 7.5 seconds. As the star rotated, the emitting region came into and out of view, creating regular pulses in the declining tail of the flare. This pulsation allowed astronomers to confirm that the emission came from a localized region on or near the surface, rather than from the entire star uniformly. The pulsating tail continued for several minutes, gradually fading as the star's activity decreased following the main event. The mechanism that produces such enormous energy release in such a brief time remains a subject of active research, though the general picture is becoming clearer. Giant flares likely involve a catastrophic reconfiguration of the magnetic field, not just a simple crustal fracture, but a wholesale rearrangement of field geometry. The twisted field lines that store energy in the magnetosphere may suddenly reconnect, releasing their stored energy in a process similar to but far more extreme than solar flares. The crust may fracture extensively at the same time, contributing to the total energy release through its own elastic energy. The 2004 event was not the first giant flare detected from a magnetar, though it remains the most powerful observed to date. The first recognized giant flare occurred on the 5th of March, 1979, from a magnetar now known as SGR 0526, located in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, roughly 160,000 light-years distant. This flare initially caused confusion among scientists, who did not immediately recognize its source as a type of neutron star with extreme magnetic properties. The understanding of magnetars as a distinct class of objects grew partly from studying this event and its implications. A second giant flare occurred on the 27th of August, 1998, from the magnetar SGR 900+14, located approximately 20,000 light-years away in our own galaxy. This event affected spacecraft in Earth orbit, temporarily disrupting some satellites and requiring adjustments to their operations. The 1998 flare helped establish the pattern of giant flare behavior and provided additional data for understanding the physical mechanisms involved. Together with the 1979 and 2004 events, it forms the complete sample of confirmed giant flares from which scientists must draw conclusions about these extreme phenomena. The rarity of giant flares means that each observed event provides irreplaceable information about magnetar physics under extreme conditions. With only 3 confirmed events spread over several decades, statistical understanding is limited, and each new flare significantly improves our knowledge. Astronomers maintain monitoring programs specifically designed to catch the next giant flare, whenever and wherever it might occur. The wait may be years or decades, but the scientific value of detecting and studying such an event justifies patient observation. The energy reservoir that powers giant flares is the magnetic field itself, the same reservoir that powers ordinary starquakes, but tapped far more dramatically. The field contains enough energy to power thousands of giant flares in principle, but the actual number will be much smaller since the star's active lifetime is limited. After each giant flare, the magnetar continues to exist with a somewhat weaker field, still capable of ordinary bursting activity, but perhaps less likely to produce another giant event soon. The field strength and configuration determine the potential for future extreme events. Between the December 2004 flare and the present day, no additional giant flares have been confirmed from magnetars in our local group of galaxies. Candidates have been identified in more distant galaxies, short bursts that could represent giant flares too far away to show the detailed behavior visible in nearby events. If these distant candidates are indeed giant flares, they suggest that such events may be more common throughout the universe than our local sample indicates. The universe may frequently host these extreme releases of energy, visible briefly across intergalactic distances, before fading. The space around a magnetar, where giant flares and ordinary bursts originate, presents an environment shaped entirely by the extraordinary magnetic field. The region immediately surrounding the star, called the magnetosphere, contains charged particles trapped by the field, radiation flowing along field lines, and energy stored in twisted field configurations. Understanding this environment helps explain how the energy released in flares and starquakes is converted into the radiation we observe from across the galaxy. The magnetic field of a magnetar does not simply extend outward in smooth, simple curves, but rather forms a complex environment that shapes everything in the region surrounding the star. This environment, called the magnetosphere, begins at the stellar surface and extends outward to distances where other influences begin to compete with the magnetic field's dominance. Within this region, the field determines how particles move, how radiation propagates, and where energy accumulates before eventual release. The magnetosphere serves as the arena where the magnetar's most observable behaviors take place. Close to the surface, the magnetic field achieves its greatest strength, the lines of force emerging from the crystalline crust and rising into the surrounding space. If we could visualize these field lines as glowing threads, they would appear as dense bundles near the magnetic poles, spreading outward and curving around toward the equator. The field geometry might be relatively simple, resembling the familiar pattern of a bar magnet, or it might be twisted and complex, with field lines wound around each other in configurations that store enormous energy. Most magnetars probably have fields somewhere between these extremes, with some twisting and complexity, but also some underlying order. Charged particles in the magnetosphere, electrons, positrons, and ions are forced to follow the magnetic field lines rather than traveling freely in any direction. The field is so strong that particles cannot move perpendicular to the lines. Instead, spiraling tightly around them while drifting along their curves. This forced motion concentrates particles in certain regions and depletes them from others, creating structure within the magnetosphere that affects how radiation is emitted. The particles gyrate around the field lines at tremendous speeds, and this gyrating motion produces radiation that contributes to the magnetar's overall emission. The energy stored in a twisted magnetic field provides the power source for much of the magnetar's activity, beyond simple thermal emission from the hot surface. When field lines are twisted or wound around each other, they contain magnetic energy that can be released if the configuration changes. This is similar in principle to a wound spring or a twisted rubber band, though the energies involved are incomparably greater. The accumulation of twist in the magnetic field, driven by processes in the star's interior, represents the loading of energy that will eventually be released in bursts and flares. The release of magnetic energy can happen gradually, powering the persistent X-ray emission that makes magnetars visible between bursts, or suddenly in the flares and giant flares we have already explored. During sudden releases, the field lines may reconnect, snapping into new configurations that contain less stored energy, with the difference converted to particle acceleration and radiation. This magnetic reconnection process occurs in more modest forms on the Sun, driving solar flares, but on magnetars, it proceeds under far more extreme conditions. The fundamental physics is the same, but the scale and intensity differ by many orders of magnitude. The region where the magnetic field dominates extends outward to a boundary called the light cylinder, where the field lines would have to rotate faster than light to remain connected to the rotating star. Beyond this boundary, the field must disconnect and flow outward as electromagnetic radiation, carrying energy away into space. For magnetars, which rotate slowly compared to ordinary pulsars, the light cylinder lies relatively close to the star, perhaps a few thousand kilometers away. Within this region, the magnetosphere maintains its connection to the star. Beyond it, energy flows outward and is lost. Particles accelerated in the magnetosphere can reach enormous energies, far exceeding anything achievable in human-built accelerators. Though the number of such particles is small, these particles radiate as they accelerate and gyrate, producing the X-rays and gamma rays that we observe from magnetars across the galaxy. The spectrum and intensity of this radiation carries information about conditions in the magnetosphere, the field strength and geometry, and particle populations that produce it. Decoding this information requires sophisticated models of magnetospheric physics, models that continue to be refined as observations accumulate. The magnetosphere is not static, but evolves as the star rotates, as the magnetic field configuration changes, and as particles are injected, accelerated, and lost. On timescales of seconds, the rotation carries different parts of the magnetosphere through our line of sight, creating the pulsations observed in magnetar emission. On timescales of months and years, the overall field configuration may change due to processes in the interior, altering the magnetospheric structure and the emission it produces. This dynamic character makes magnetospheres challenging to model, but also rich in information for those who study them carefully. The interaction between the magnetosphere and the interstellar medium surrounding the magnetar creates additional observable effects, though these are more subtle than the direct emission. The magnetar's strong field can influence the space around it to distances far exceeding the magnetosphere proper, sweeping through the surrounding gas and potentially creating shocks. The wind of particles and radiation from the magnetar carries energy outward, depositing it in the nearby environment over time. Some magnetars are associated with nebulae, or shells of material that have been shaped by this interaction over thousands of years. The magnetosphere during a giant flare must behave very differently from its usual state, with field lines reconfiguring catastrophically and particles accelerated to extreme energies in large numbers. The gamma rays and X-rays released during a giant flare carry information about these extreme conditions, information that astronomers work to decode from the observed spectra and light curves. Comparing the brief extreme emission during flares to the persistent, gentler emission between flares reveals how the magnetosphere responds to different energy inputs. These comparisons help build our understanding of the physics governing this extraordinary environment. Between bursts and flares, the magnetosphere settles into a relatively stable configuration, emitting steadily as the star rotates and hot particles stream along field lines. This quiescent emission represents the baseline state of the magnetar, the background against which bursting activity appears as temporary increases. Monitoring this persistent emission over time reveals gradual changes in the magnetar's state, trends in its cooling, its spin down, and its magnetic field evolution. The magnetosphere serves as a window into the star's condition, visible from across the galaxy to instruments sensitive to its X-ray glow. Observing magnetospheres and the radiation they produce requires instruments capable of detecting X-rays and gamma rays, forms of light that cannot penetrate Earth's atmosphere. Space-based telescopes, orbiting above the atmosphere, collect these high-energy photons, building up images and spectra over hours and days of observation. The technology that makes magnetar observation possible represents decades of engineering development, placing sensitive detectors in orbit where they can function without atmospheric interference. Understanding how we observe magnetars helps appreciate the effort that has gone into building our current knowledge of these remarkable objects. The observation of magnetars requires looking beyond the forms of light our eyes can perceive, into wavelengths that carry far more energy per photon. X-rays and gamma rays, the primary forms of radiation emitted by magnetars, possess wavelengths far shorter than visible light, and energies thousands to millions of times greater. These energetic photons interact strongly with the atoms in Earth's atmosphere, never reaching the surface, where ground-based telescopes might detect them. To observe magnetars, we must place our instruments above the atmosphere, in orbit around Earth or on high-altitude balloons, looking outward from a clearer vantage point. The first satellites capable of X-ray astronomy were launched in the 1960s, opening a new window on the universe that revealed objects invisible at other wavelengths. Early X-ray missions detected numerous point sources scattered across the sky, many of which would later be identified as neutron stars in various forms. The instruments on these early satellites were crude by modern standards, but they established that the X-ray sky was rich with sources worth studying. Among these sources were objects that would eventually be recognized as magnetars, though understanding their true nature would require decades of additional observation. Modern X-ray observatories, including missions with names like Chandra, XMM Newton, and Swift, provide the detailed data astronomers use to study magnetars today. Chandra, launched in 1999, can produce sharp images in X-rays, distinguishing individual sources and mapping their spatial structure with remarkable precision. XMM Newton, a European mission launched the same year, emphasizes sensitivity and spectroscopy, collecting many photons and spreading them by wavelength to reveal composition and physical conditions. SWIFT, designed to catch transient events like gamma-ray bursts, responds rapidly to magnetar flares, pivoting to observe within seconds of detecting a burst. The detection of magnetars typically begins with observing their persistent X-ray emission, the steady glow from the hot surface visible between bursting episodes. This emission provides information about the surface temperature, which usually lies around a few 100 million degrees for the youngest and most active magnetars. The temperature exceeds what most other neutron stars maintain, indicating an internal heat source beyond simple cooling from the star's formation. This extra heat comes from the decaying magnetic field itself, which releases energy as it evolves, maintaining elevated temperatures throughout the magnetar's active lifetime. Bursts from magnetars appear as sudden increases in X-ray and gamma-ray brightness, sometimes exceeding the persistent emission by factors of thousands or more. Detecting these bursts requires monitoring instruments that watch large portions of the sky continuously, catching the flash whenever and wherever it occurs. Several satellites carry instruments designed for this all-sky monitoring, including Fermi, which launched in 2008, and the older SWIFT mission. When these monitors detect a burst, they alert other telescopes and instruments to observe the source for detailed follow-up study. The rotation period of a magnetar is measured by looking for regular variations in its X-ray emission, as different parts of the surface rotate into and out of view. Hot spots, or magnetically active regions on the surface, emit more strongly than surrounding areas, creating a lighthouse-like effect as the star spins. By timing these periodic variations precisely over weeks and months, astronomers determine the rotation period to many decimal places of precision. Magnetars typically rotate once every few seconds to several seconds, far slower than the millisecond periods of the fastest pulsars, but still fast by human standards. The spin-down rate, measuring how quickly the rotation slows over time, provides crucial information about the magnetic field strength that cannot be observed directly. A stronger magnetic field exerts more torque on the rotating star, causing faster spin-down, which is why magnetars slow down more rapidly than ordinary pulsars. By measuring both the rotation period and its rate of change, astronomers can infer the surface magnetic field strength using well-established formulas from electromagnetism. These inferred field strengths confirmed that magnetars possess extraordinarily strong fields, supporting the theoretical predictions that motivated their identification as a distinct class. Glitches in the rotation, sudden small increases in the spin rate, reveal star quakes and other internal processes that redistribute angular momentum within the star. These glitches appear in the timing data as discontinuities, the period suddenly decreasing by a tiny fraction before resuming its gradual increase. By cataloging glitches over years of observation, astronomers build understanding of crustal properties and the rate of magnetic stress accumulation. The patterns of glitching behavior differ among individual magnetars, reflecting their different magnetic field strengths, ages, and internal configurations. Radio observations of magnetars were long thought to be impossible, since the extreme magnetic field was expected to suppress the radio emission process. In 2006, astronomers unexpectedly detected radio pulses from a magnetar for the first time, challenging this conventional wisdom. The radio emission turned out to be transient, appearing during active periods and fading when the magnetar quieted down, unlike the steady radio beams of ordinary pulsars. This discovery opened a new avenue for studying magnetars, allowing ground-based radio telescopes to contribute alongside space-based X-ray observatories. The connection between magnetars and other classes of neutron stars took decades to establish, as different observational characteristics initially led to different classification schemes. Objects called soft gamma repeaters, identified by their repeated bursts of soft gamma rays, were eventually recognized as magnetars in their active bursting phases. Similarly, anomalous X-ray pulsars, which showed unusually strong X-ray emission for their apparent age, turned out to be magnetars viewed at different stages or orientations. The unification of these separate classes under the magnetar framework represented a major step forward in understanding, achieved through years of observational and theoretical work. The approximately 30 confirmed magnetars currently known represent only those actively emitting at detectable levels, at X-ray wavelengths, and within observing range of our telescopes. Many more magnetars likely exist in our galaxy, but are too distant, too faint, or too old and quiet to be detected with current technology. The true population may number in the thousands or tens of thousands, scattered throughout the Milky Way in the remnants of massive stars that died throughout galactic history. Each confirmed detection adds to our sample, improving statistical understanding of magnetar properties and behavior. Individual magnetars show distinct personalities despite sharing the defining characteristic of extreme magnetic fields. And studying several specific objects helps illustrate the range of behaviors observed. Some magnetars burst frequently, with dozens of events recorded over years of observation, while others remain quiet for long periods. Some have experienced giant flares, while most have not, or at least not while we have been watching. Exploring a few well-known magnetars individually reveals the diversity within this small but remarkable population. The magnetar that produced the extraordinary flare of December 2004 has become one of the most studied objects in high-energy astronomy, drawing attention for both its extreme behavior and what it reveals about magnetar physics. This object, designated SGR 1806-20, lies approximately 50,000 light-years from Earth, on the far side of our galaxy. The distance makes detailed observation challenging, but the sheer power of its emissions ensures that it remains detectable despite the intervening gas and dust that block visible light. Among known magnetars, this one possesses perhaps the strongest magnetic field yet measured, estimated at roughly 2 quadrillion Gauss. Before the giant flare of 2004, this magnetar had already drawn attention for its frequent bursting activity and its unusually powerful, persistent emission. The object produced numerous smaller bursts over the years leading up to the giant flare, establishing itself as one of the most active magnetars under observation. This high activity level suggested that significant magnetic stress was accumulating within the star. Stress that would eventually find release in the catastrophic reconfiguration of December 2004. Whether the giant flare could have been predicted from the precursor activity remains an open question, complicated by the limited statistics available from only a few such events. The magnetar SGR 1900 plus 14 provided the second confirmed giant flare in August 1998, an event that affected spacecraft in Earth orbit despite the object lying 20,000 light-years distant. This magnetar sits in our own galaxy, closer than SGR 1806-20, but still far enough that individual surface features cannot be resolved with any current instrument. The 1998 flare temporarily disrupted satellites and required operational adjustments, demonstrating that even events occurring halfway across the galaxy can have tangible effects in our vicinity. Since its giant flare, this magnetar has continued to produce smaller bursts, remaining one of the more active sources under regular monitoring. The magnetar located in the Large Magellanic Cloud, SGR 0526-66, holds historical significance as the source of the first recognized giant flare on the 5th of March, 1979. The Large Magellanic Cloud is a satellite galaxy of the Milky Way, visible in the southern sky as a fuzzy patch roughly 160,000 light-years away. Despite this enormous distance, the flare was powerful enough to be detected by gamma-ray instruments of that era, causing initial confusion about the nature and location of the source. Understanding that this burst came from a magnetar in another galaxy took years of analysis and the development of the theoretical framework needed to explain such extreme events. A magnetar, designated XTEJ 1810-197, discovered in 2003, became notable as one of the first magnetars detected as a radio source. The transient radio emission from this object appeared during an active phase and provided a new avenue for studying magnetar physics using ground-based radio telescopes. The radio observations revealed properties of the magnetosphere that complement X-ray observations, offering a fuller picture of conditions around the star. This magnetar helped establish that radio emission from magnetars, while rare and transient, is possible and worth searching for in other objects. Perhaps the most intriguingly located magnetar sits very close to the supermassive black hole at the center of our galaxy, designated SGRJ 1745-2900. This object orbits within a fraction of a parsec of the central black hole, experiencing gravitational effects that influence its observable behavior. The proximity to Sagittarius A star, the name given to the central black hole, creates a unique laboratory for studying how magnetars behave in extreme gravitational environments. The magnetar's signals, as observed from Earth, are affected by the curved space-time around the black hole, providing tests of physics impossible to conduct anywhere else. The variety among known magnetars extends beyond their locations to include differences in rotation period, magnetic field strength, activity level, and age. Some magnetars rotate in just a few seconds, while others take 12 or more seconds per rotation, spanning a range that reflects their different evolutionary states. The inferred magnetic field strengths vary by factors of several, with the strongest approaching 1 quadrillion Gauss, and the weakest barely exceeding typical pulsar values. Activity levels range from nearly continuous bursting to years of quiescence, interrupted by rare outbursts. The ages of observed magnetars span a range from very young objects still embedded in supernova remnants to older objects whose connection to their birth events has become difficult to trace. Young magnetars often sit near the centers of supernova remnants, visible as expanding shells of gas ejected during the explosion that created the neutron star. The association with remnants provides independent age estimates, confirming that magnetars are typically young objects, thousands to perhaps tens of thousands of years old. Older magnetars, their remnants having faded and dispersed, must be identified solely by their own properties. Several magnetars have been found in association with massive star clusters, collections of recently formed stars from which the massive progenitors of neutron stars would naturally originate. These associations support the picture of magnetars forming from massive stars, stars that live fast and die young, remaining near their birthplaces when they explode. The connection between magnetar locations and regions of recent star formation strengthens our understanding of the progenitor stars and the conditions that produce magnetar-grade magnetic fields. Mapping the distribution of magnetars through the galaxy tests theories of stellar evolution and the magnetar formation process. Among the known magnetars, new discoveries continue to add members at a slow but steady pace, as monitoring instruments detect outbursts from previously quiet objects. Each new magnetar provides additional data for understanding the population as a whole, contributing to statistical studies of field strengths, rotation periods, and activity patterns. The current sample of about 30 objects is small by astronomical standards, limiting the conclusions that can be drawn, but each addition helps refine the picture. Future monitoring programs with more sensitive instruments will likely expand the known population significantly, revealing magnetars too faint or too quiet for current detection. The known magnetars represent the visible tip of a much larger population whose full extent remains uncertain. Objects scattered through our galaxy and beyond in numbers we can only estimate. Understanding this larger population requires moving beyond the individual objects to consider magnetars in their cosmic context, their formation rates, their lifetimes, and their possible connections to other energetic phenomena in the universe. The population of magnetars in our galaxy extends far beyond the handful of objects actively emitting at detectable levels, encompassing a much larger number that have faded below observational thresholds. Estimates suggest that the Milky Way might contain anywhere from 10,000 to 100,000 magnetars, most of them old and quiet, their intense magnetic fields long since decayed. The approximately 30 confirmed magnetars represent only those young and active enough to produce the X-ray emission and bursts that draw our attention. The larger population remains invisible. Neutron stars like any other, but distinguished by their histories as former magnetars now faded into obscurity. The formation rate of magnetars depends on how many massive stars die as supernovae, and what fraction of those produce magnetars, rather than ordinary neutron stars or black holes. Supernovae occur in our galaxy roughly 2 or 3 times per century, each one potentially creating a neutron star if the progenitor mass falls within the appropriate range. If perhaps 10% of neutron stars become magnetars, then one new magnetar might form every few hundred years, joining the population as older magnetars fade below detection. These rates remain uncertain, estimated from limited observations and theoretical models, rather than direct counts. The active lifetime of a magnetar, the period during which it produces detectable X-ray emission and bursts, is thought to last roughly 10,000 years or so. During this time, the magnetic field remains strong enough to stress the crust and power bursting activity, generating the emission that brings magnetars to our attention. After this active phase, the field weakens to levels comparable to ordinary pulsars, and the distinctive magnetar behavior ceases. The former magnetar continues to exist as a neutron star, cooling slowly over millions of years, but no longer producing the emission that would identify it as a magnetar. The fraction of neutron stars that become magnetars, rather than ordinary pulsars, relates to conditions during the collapse that forms them, conditions that remain incompletely understood. Stars with certain properties, perhaps rapid rotation at the moment of core collapse, or strong magnetic fields in the progenitor core, might preferentially produce magnetars. The exact recipe remains uncertain, with different models predicting different outcomes and observational tests proceeding slowly due to the rarity of events. Understanding why some neutron stars become magnetars would illuminate both stellar evolution and the physics of matter under extreme conditions. Beyond our galaxy, magnetars presumably exist in similar abundances throughout other spiral galaxies that host ongoing star formation and therefore ongoing massive star deaths. Giant flares from distant magnetars may have been detected as short gamma-ray transients too far away to show the detailed structure visible in nearby events. If these candidate events are genuine giant flares, they imply that such events occur frequently throughout the universe, appearing briefly from distances of millions of light years. The cosmic rate of giant flares may significantly exceed what our limited local sample suggests, with events occurring somewhere in the observable universe quite often. The connection between magnetars and other high-energy transient phenomena has become an area of active investigation, with several possible links under study. Fast radio bursts, mysterious millisecond pulses of radio emission arriving from cosmological distances, have been proposed as emissions from distant magnetars. This hypothesis received dramatic support in April 2020, when a magnetar in our own galaxy produced a burst that resembled an extragalactic fast radio burst. The burst from SGR 1935 plus 2154 demonstrated that magnetars can produce fast radio burst-like emission, though whether all such bursts come from magnetars remains debated. Some unusually energetic supernovae may be powered by rapidly rotating magnetars born in the explosion, providing extra energy beyond what the explosion itself would release. These superluminous supernovae shine 10 to 100 times brighter than typical supernovae, requiring an additional power source that a millisecond magnetar could provide. The rapidly spinning magnetar would radiate away its rotational energy over days and weeks, pumping that energy into the expanding supernova debris. The resulting display would outshine ordinary supernovae, briefly becoming visible across significant fractions of the observable universe. Gamma-ray bursts, the most energetic explosions known to occur in the universe, may also involve magnetar formation in certain cases. The short gamma-ray bursts, lasting less than 2 seconds, are thought to result from neutron star mergers, which could produce magnetars in some cases. A magnetar formed in such a merger would last only briefly before collapsing to a black hole, but during that brief interval might power observable emission. The connection between magnetars and gamma-ray bursts remains an active area of research, with new observations regularly adding pieces to the puzzle. The distribution of magnetars through our galaxy follows the distribution of massive stars concentrated toward the galactic center and the spiral arms, where star formation is most active. This correlation supports the picture of magnetars forming from massive progenitor stars, which live short lives and die near their birthplaces. Magnetars found far from known star-forming regions may have been kicked to high velocities during the supernova that created them, traveling far from their origins over millions of years. The observed distribution contains information about both formation locations and subsequent motion through the galaxy. The possibility that magnetars might pose hazards to life on distant planets remains a matter for careful analysis rather than concern. A giant flare from a magnetar within 10 light-years could indeed damage a planet's ozone layer and affect surface life, but no magnetars are known within this dangerous radius. The nearest known magnetar lies thousands of light-years away, far enough that even giant flares produce no harmful effects on Earth, beyond the measured but harmless ionospheric disturbance. The universe places many hazards at distances that make them astronomically interesting, but practically irrelevant to daily life. Each magnetar will eventually fade as its magnetic field decays and its activity diminishes, following a path from extreme youth toward quiet age. The energy stored in the magnetic field slowly converts to heat and radiation, powering the active phase while also depleting the reservoir that makes it possible. Understanding this evolution from bright youth to dim old age helps predict what future magnetars will look like and what the undetected population might contain. The fate of magnetars unfolds over thousands of years, far longer than our few decades of observation, requiring models and inference to project what we cannot directly watch. The magnetic field that defines a magnetar does not persist indefinitely, but slowly weakens over thousands of years, releasing its stored energy through bursts, flares, and persistent emission. This decay represents the gradual depletion of what makes a magnetar special, the transformation from an extraordinary object to an ordinary neutron star. The process occurs too slowly for us to observe directly in any individual object, unfolding over timescales vastly longer than human civilization has existed. Instead, we understand it through theoretical models and by observing magnetars at different apparent ages, building a picture of how these objects evolve. The mechanisms that cause the magnetic field to decay involve complex interactions between the field and the matter in the star's interior. The field may dissipate through electrical currents flowing in the crust and core, currents that lose energy to resistance over time, despite the superconducting properties of some interior regions. The field configuration may also evolve through processes that bring differently magnetized regions into contact, allowing the field to reorganize into lower energy states. Both dissipation and evolution contribute to the weakening, their relative importance depending on conditions that vary from star to star. The energy released by field decay does not simply vanish, but heats the star's interior, maintaining elevated surface temperatures long after formation heat would have radiated away. This ongoing heating explains why magnetars remain hotter than their ages would suggest, based on formation heat alone, appearing younger than they actually are when temperature is used as an age indicator. The heating rate decreases as the field weakens, allowing the star to eventually cool as ordinary neutron stars do. The connection between magnetic field strength and surface temperature provides a way to study field decay indirectly through temperature measurements. The active phase of magnetar behavior characterized by bursts and flares, gradually diminishes as the magnetic field weakens below the levels needed to stress the crust to breaking. The frequency of bursts decreases, and the energy released in each burst diminishes as the reservoir of magnetic energy becomes depleted. Eventually, the bursting ceases entirely, and the object no longer produces the emission that would identify it as a magnetar to observers. The transition from active magnetar to quiet neutron star occurs gradually rather than suddenly, a slow fade rather than an abrupt stop. The rotation rate continues to slow throughout this process, the magnetic field still extracting angular momentum from the spinning star, even as its strength diminishes. The spin-down rate decreases as the field weakens, the torque falling along with the field strength, according to well-established electromagnetic relationships. Eventually, the magnetar's rotation period may stretch to tens of seconds or longer, far slower than the millisecond periods of the youngest pulsars. The spin-down itself represents energy loss, converting rotational kinetic energy to outgoing electromagnetic radiation. After perhaps 100,000 years, the former magnetar resembles an ordinary neutron star more than the extreme object it once was. The magnetic field has decayed to levels typical of standard radio pulsars, perhaps a trillion Gauss rather than a quadrillion. The bursting activity has ceased, the surface has cooled, and the rotation has slowed to periods unremarkable among the neutron star population. Nothing about the object would suggest its past as one of the most extreme magnetic environments in the universe. Its history, recorded only in subtle aspects of its composition or structure. The cooling continues for millions and then billions of years, the surface temperature dropping from millions of degrees to thousands, and eventually toward absolute zero. No object in the universe has cooled long enough to reach truly cold temperatures, as the universe itself is only 14 billion years old. The oldest neutron stars have had time to cool significantly, but remain warm by the standards of ordinary room temperatures. They persist essentially forever, compact remnants of stars that died long ago, carrying mass that will never change significantly through any known process. The final state of a former magnetar is a cold, dark sphere, smaller than a city, but more massive than the Sun, drifting through the galaxy with minimal interaction with its surroundings. The object no longer emits detectable radiation, no longer affects its environment significantly, no longer produces any of the phenomena that once made it remarkable. It simply exists, a ball of compressed matter following its orbit around the galactic center, unchanged by the passage of time. Trillions of years from now, it will remain essentially as it is today, a silent record of a massive star that died in a spectacular explosion and left behind this dense remnant. The universe contains these objects in unknown numbers, former magnetars and former pulsars and neutron stars that never showed special properties, scattered through every galaxy that has hosted star formation. They form a silent population, invisible to most observations, but collectively representing a significant fraction of the matter that once shone as stars. The cosmos accumulates these remnants over billions of years, the ashes of stellar fires that have burned out but whose embers persist indefinitely. Each one carries the compressed core of what was once a brilliant star, reduced to a compact ball that time cannot further simplify. The magnetars we observe today represent a tiny window in the lives of these objects, the brief youthful phase when they blaze with activity visible across galactic distances. This active phase lasts perhaps 10,000 years out of existences that will continue for far longer than the current age of the universe. We happen to live at a time when the instruments exist to detect these objects, and enough have been observed to recognize them as a distinct class. Future observers, millions or billions of years from now, would find the same population of magnetars being born and fading, the cycle continuing as long as massive stars form and die. The study of magnetars reveals what physics allows under conditions impossible to create on Earth, demonstrating the extremes of magnetic field strength and matter compression. These objects exist because the universe permits them, because the laws of nature do not forbid their formation and persistence. The knowledge we gain from observing them extends our understanding of electromagnetism, nuclear physics, and gravitation, tested under conditions that amplify subtle effects into observable phenomena. Each magnetar is a laboratory beyond anything we could construct, conducting experiments in extreme physics and broadcasting the results to anyone watching. The night sky contains these objects among its many wonders, points of X-ray light marking locations where extreme physics occurs continuously. From our comfortable distance, we observe without risk, learning about conditions that would prove instantly incompatible with any form of matter we know. The magnetars themselves neither know nor care about our observations, simply existing as physics requires, producing the phenomena we detect as natural consequences of their properties. They represent what the universe creates when gravity and magnetism and quantum mechanics combine in certain ways. Remarkable outcomes of ordinary rules operating under extraordinary circumstances.